Good evening to all of you. Today is our lecture based on vector spaces, and this is chapter number 4, and it is a half part of chapter 4, and the second half part of chapter 4 we will discuss in week number 6. So this is week number 5, and there are here we discuss the 5 points, and rest of the points we will discuss on later on week 6. So because of this is a big chapter. Yes. So I'm going to start this lecture. So these are our main points. As we discussed that a vector space can be defined like this: a sequence of n real numbers x1, x2, xn, or in n space, the set of all ordered n tuples is. So in first dimension, in one dimension, R1 n, if n is equal to 1, then it is a first space or set of all real numbers. And in second dimension, or we say in R2 or second space, so the in second space we say set of all ordered pair of real numbers x1, x2. Ordered pair of real numbers x1, x2, and we have numbers like minus infinity to plus infinity. And if we are talking about three-dimension space, three-dimension space, n is equal to 3, or we say r cube, to set of all ordered triple of real numbers x1, x2, x3. So x1 is a x coordinate, y coordinate, and this is a z coordinate. And similarly, n is equal to 4, 4 space, 5 space, 6 space. So there are n space we can represent in a vectors. So previously we know that how we can represent a point on a graph, but in a vector space we see how we can represent a vector in a plane. If we have a plane, then how we can represent a vector. Also, a vector have some base and some head, and there is some tail of vector, and it is denoted by like this, from 0, 0 to x1, x2. So it is a vector. So vectors can be defined with the if there are two vectors. In some books we define a vector with the bold letter, like u is a bold, or in some books it is defined like u, and in upper side of u there is a small arrow. So it is a vector u, and it is a vector v. So there are some authors use different notations, but in our book it shows whenever we discuss about the vector, it will bold, and the letter is little bold. Here the letter is little bold, little dark. So whenever the little dark letter appears, it means that it is a vector. But in your exam, when you are going to write, because of the bold letter we cannot write in a copy, so you always write like this. Whenever you define a vector, you always like this u, and upper there is an arrow. So with the help of this I can understand that it is a vector. So vector can be defined if for example, if it is in 2 dimension, then it can be defined u1, u2, un. U1, U2. If it is in 3 dimension, then we can define U1, U2, U3. So U1, U2, U3. If n dimensions, we can define U1, U2, Un. So these are the tuples of the vector. So and the two vectors are said to be equal if we say that vector u is equal to vector v. So if and only if all the tuples of the vectors are equal, meaning is that u1 equal to v1 and u2 is equal to v2 and u3 is equal to v3 and so on, then we say that the vectors are equal. And if we are going to add the two vectors, the similarly the if you are going to add then u1 add to v1 and u2 add to v2 and u3 add to v3. So this is the criteria to add the two vectors. Similarly, the subtraction of two vectors is u1 minus v1 and u2 minus v2 similarly. And if you are going to multiply the vector with some constant c, then it is multiplied with each and every element of the vector, each and every component of the vector. So the sum of two vectors and their scalar multiple of a vector in Rn are called standard operations in Rn. So again, if we are going to multiply with multiply with a constant -1, if -1 u, that is minus u1 minus u2 minus un. So the difference of two vectors u1 as it is. When you are going to multiply, when you are going to add, similarly you can subtract. You can, so, okay. So u1 minus v is equal to u1 minus yani every tuple subtract with the every tuple. Similarly u2 subtract v2. So this is a method to do the addition, subtraction, multiplication. Now there is another thing, that is a zero vector. Zero vector is defined by 0 0. If it is in two dimension, then we say that 0 is equal to 0 0. And if it is in three dimension, we say 0 is equal to 0 0 0. Similarly, n dimensions, we say that it is 0 up to n. So this is a vector, and in a copy I define like this: 0 upper side there is an arrow, so it is a vector 0. But in our book we define with the bold letter. So the zero vector 0 Rn is called the additive identity in Rn. So the vector minus v is called the additive inverse of v. So the properties of a vector addition and scalar multiplication, these are the properties of vectors. So commutative law holds and associative law holds and 0, but if we are going to add with 0, so there are some properties of a vector. So these 10 properties. So there is an operations, vector operation. So it is given that, for example, we have given that one vector is in 4 dimension. The value of u is given this, and the value of v is given, and the value of w is given this. And in R4, of course, we have 4 element 1 2 3 4. So it is an R4. So the question is solve x for x in each of the following. So x is equal to 2u minus v plus 3w. So let's see how we can add, how we can open the bracket, and how we can solve this a part. So in a part, so first of all I write 2u minus v plus 3w. So first of all I open the bracket and write in the standard form 2u minus v plus 3w. So first of all I will multiply 2 inside the u. So we know our u is 2 minus 1 5 0. So we multiply 2 inside this. So 2 multiplied by 2 is 2 to the 4, and 2 multiplied by minus 1 is minus 2. 2 multiplied by 5 is 5 to the 10, and 0 0. So we get this 2u. Then again v multiplied by minus 1. So I am going to multiply v with minus 1. So everywhere over here we see that we multiply with minus, and after that we are still we are not multiply. We after that I will multiply. I still minus sign is outside. Now the third one is minus 3w. So minus 3 put inside. So our W is minus 6203. So 3 6 are 18 and 3 2 are 6 and 3 zeros are 0 and 3 3 are 9. So if we get this thing. Now next time what I do, I will add all these things. So first of all, I will add the element on ith element to ith element. As I told you, when we are going to add or subtract, then every element, ith element to, if we are going to add, then add ith element to ith element and jth element to jth element, kth element to kth element. So it is our ith element. This is our ith element. This is our ith element. So add these things. So so we are going to add these three. We get this. Similarly, now adding jth element to jth element. This is our jth element to jth element, jth element to jth element. So we get this. Similarly, now add next kth element to kth element. This is kth element and this is kth element. So if we get this. Similarly, next L element, this element and this element. So we are going to add this, and finally we get this vector. So this is the value of x, y, z. So this is the vector x, the value of vector x. So hopefully you understand this, how we can add the vectors, how we can add, how we can subtract, how we can multiply. Similarly, we can do another example, example number B. So hopefully you can understand, or you can do by yourself. So in the next slide, I will show you how we can solve. The method is same as you see. And over here, one by one, step by step, I will show you. These things are explained, and you will see at your home how we can add these things. And we get a vector x is equal to x component, y component, z component, and next component, fourth component. So this is the procedure. Now next, properties of additive identity and additive inverse. These are six properties of additive identity is unique. U plus v is equal to v, and inverse u plus v is equal to 0 if u is equal to minus v. And if you multiply with a vector with a 0, then we get a 0 vector. If we multiply a vector with a constant, then we get a 0 vector. So if we multiply a vector with a constant and we get a 0, then one thing is possible: either the constant is 0 or the vector is 0. And if we multiply a minus into minus with a vector, we get a plus vector. So these are the additive identities. And the next thing is linear combination. So what is linear combination? When we have given some vectors v1, v2, vn, and we have given some constants c1, c2, cn, and if we are going to multiply the vectors with the constant like this, x is equal to c1 v1, c2 c2, cn vn, if these things are happens, then we say that in after 5 to 6 slides, I will show you what is the use of linear combination. There is a use of linear combination to find the linear dependence or linear independence. So this is, we have to know that what is linear combination. So to find the linear dependence, if we are going to find linear dependence, first of all we have to do this thing, linear combination. So after 5 to 6 slides, I will show you how we can find the linear dependence and linear independence. So but before that, there is an example of linear combination, a very simple example. Here is given a vector x is in 4 dimensions, and the value of u, this is a vector u and this is a vector v. and vector W. There are three vectors are given U, V, W in R3. Find A, B, C such that X is equal to AU plus BV plus CW. So these things are given, and the question is find the value of AU plus BV minus CW plus CW. So first of all, I write AU. First of all, I write AU. AU is we have A multiply with U. U meaning Uth element of I. So I multiply A into 0. So we get uh, A into 0 over here. We get A into 0. We get A into 0. Again plus, then next time I multiply B into V. So B into V, the ith element of V is -1. So this is second element, B into V. Similarly, the third element, I have to multiply C into W. So C into W, the ith element of W is 3. So C into W. Here is C into 3C. And it will is equal to minus X is equal to -1. It is equal to -1. So it is equal to -1. So the ith element is complete. Now second, we will move to jth element. So again I move AU. I will go to AU. So A and Uth element is U of jth element is 1. So A into 1 again plus BV. So B into V, the element of V, jth element of V is 1. So I write B. Similarly, CW. C is and C and the jth element of W is 1. So it is 1. So and the right hand side of jth element is 2. This is 2. So I write -2 over here. Similarly, similarly I write and the kth element kth element. Similarly, I can write this equation, and after that I will, with the help of we have three equations: equation number 1, equation number 2, and equation number 3. We have three equations and three unknown, so we know how we can find the value of A and B and C. So there are so many methods we can find the value. Either solve equation number 1 and 2 and solve equation number 2 and 3 and then find the value of A and C. Or there is some another method, or you can draw a matrix and with the help of, and convert the matrix into a triangular form, and you can find the value of A, B, C. So there are so many methods. Any method you can choose, there it is right. So you have to find the value of A, B, and C. So it says that a vector can be a row form or vector can be column form. Any form can be happens. Column vector, it is said the column vector, and in the row vector is said the row vector. So don't be confused about the row vector and column vector. So the matrix operation of addition and scalar multiplication give the same result as corresponding vector operation. So this is just I give you the example of addition and multiplication. If we have two column vectors and we are going to add these two column vectors, we get again the column vector. If we have a column vector, we are going to multiply with the constant, we get again this column vector. Now there are simple things. Now we are going to start our next topic, that is vector space. Till now we are discussed about the vector, but here is a different thing. It is called the vector space. So what is vector space? Let V be a set on which two operations, vector addition and scalar multiplication, are defined if the following axioms are satisfied for every u, v, and w in V, and every scalar real number C, D, then V is called a vector space. So there are 10 properties of vector space. Then with the help of these 10 properties, if these 10 properties are satisfied, then we say that it is a vector space. So we are going to define a vector space like this. If it is a vector addition and it is a scalar multiplication and it is denoted by vector, some scalar addition and some scalar multiplication. If this type of notations are written, then you directly say that it is a vector space and it satisfies the 10 points that are written over behind. So mm, the we are always right like this. V is equal to 0 is a vector space. So V plus and multiply, this type of we can write the vector space. Properties of scalar multiplication. So it is same as vector space as we observe the properties of scalar multiplication. It is same as here, no difference. And it is some examples are given whether to show that whether it is a vector space or not. To show that the set is not vector space, you need to only find one axiom that is not satisfied, because it says that we know that we have 10 axioms in a vector space. If any one axiom is not satisfied, then we directly say that it is not a vector space. So the question is, the set of all integers is not a vector space. So do you know the meaning of integer? Integer is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to infinity. These are the integers. The question says that uh, the set of all integers is not a vector space. So we take 1 point. We take 2 points. One points belongs to the vector space, and the another point we take 1 by 2. We take this point with. So now if we are going to multiply this real number and into this vector 1 by 2 and into 1, we get 1 by 2. So we observe, but 1 by 2 is not an integer. As we observe that 1 by 2 is not integer. Integers are 1, 2, 3, 4, 5, 6, but 1 by 2 is not integer. So it says that if it is not an integer, so it is not belong to vector, because of our question says that the set of all integers is not a vector space. So it is not belongs to vector space. So it is not a vector. It is not closed under addition, under scalar multiplication. So our property of multiplication is not hold in this. So we directly say that it is not a vector space. So we have to check all the 10 axioms, but here I only check only one axiom and directly say it is not a vector space. And the next thing is the subspace. Subspace basically is a part of the vector space. For example, we have a vector space, and this is a small part of the subspace. This is a subspace. So and it is a vector space. The big one is a vector space. So subspace is a part of the vector space, and it satisfies all the properties of the vector space. And there are some 2 points are extra in the subspace. The 2 points are, the first point is, so the subspace is not the empty or phi, is never empty. And the second thing is the subspace contain V, and V contains the subspace. Yeah, of course. And if big one is V, this is V, and this is W. There are two things that will contain. So V contains W, a non-empty subset. So it is called a subset, and it is also denoted by like this as W plus and dot. The same notation. Remember, a vector space we defined it V plus and multiply. It is a vector space. And similarly, a subspace we define W plus and dot. Both are the same thing. There is no any difference between a space and subspace. It cannot be empty, and it contained a vector space. Vector space contained it. So just it has 2 points. So the definition of where subspace is a vector space under the operation of addition and scalar multiplication defined in V. Then VW is a subspace of V. So these are some theorems, and it is this is some example. The set of a singular matrix is not a subspace. Let W be the set of singular matrix of order 2. Show that W is not a subspace of M2 by 2 with standard operation. So we take a matrix A is equal to 1 0, and it belongs to our subspace, and we take another matrix B is equal to this 0 0 1, and it is also belong to the subspace. But if we are going to add these two matrices, then we observe that it is a new matrix and it does not belongs to anyone, not this one and not this one. So it is not belongs to anyone. So do we directly say that it is not closed under addition? So it is not a subspace. So W2 is not a subspace of 2 by 2 space. And this is some examples we'll see. Determining the subspace in R cube. So subspace in R cube, for example, W is equal to x1 x2 and 1. X1 x2 belongs to R1. So it says that take some values. It will take 0 0 1 belongs to W in subspace, and if we are going to multiply with -1, then it is not belongs to W. So it is not a subspace. We directly say it is not a subspace because the multiplication property, inverse multiplication property, is not full. Similarly, the third problem is x1 comma x2 plus x3 comma x3. We have 3 points. First point x1, and we take a v1, v1 plus v2 and v3, because of in a question it is given that x1 comma x1 plus x3 comma x3. Similarly, we take another vector u1 and u1 plus u3 and u3. These are belongs to W. Now check whether it is closed under addition and scalar multiplication. So we know that to show it is a subspace, so we have to show there are 2 points. First point we have to show it is closed under addition, and second point we have to show it is closed under multiplication. If these 2 points are satisfied, then it is a subspace. We know that. Don't confuse it, because of we have to show, as I told you, subspace is a part of a vector space, and vector space satisfy the 10 points. If any space satisfy these 2 points or these 10 axioms, then we say that it is a vector space. And if in a question it is given that this is a subspace, and you have to it is a vector space, and you have to show that it is a subspace or not, then automatically it will satisfy all those points, and we have only to show the other 2 points, because of in this question it is given that it is a it is a vector space. It is given that V1 is a vector space and U is a vector space. It means that it satisfies all the 10 points. We only show that it is belong to the subspace or not. So we have to only show the 2 points. It is closed under addition and it is closed and under scalar multiplication. So let's recheck. First of all, I write u plus v. So I write u, yani first element of addition in first element of u and first element of this, first element of v and first element of u I write here. Then put the comma and again second element of v and second element of u. I'm going to add. This is the second element of u and second element of v. And thirdly, I write the third element of v and the third element of u. Then adding them, this is. So it is, as we observe that it is in the form like this. So it is belongs to w. And similarly, if we are going to multiply with a constant k, so kv1, kv1 plus kv2 and kv3, it is also belongs to w. So w is a subspace. There is no any difference. So w is a subspace. So these are some notations of subspace. Finding the linear combination. This is the linear combination of v1, v2. So our next topic is find the linear independent or linearly dependent. So previous slides, before 5 to 10 slides, as I told you, uh, with the help of linear combination, these are the example of linear combination. This linear combination, as I told you before 2 or 3 slides, this is called the linear combination. If we have given a vector and we are going to multiply with any constant, then we say that it is a linear combination. Before 3 to 4 slides, as I told you. Now I will show you what are the linear dependent and linear independent. So this is just the example of a linear combination. After that, I will show you. This is another example of linear combination. You will see at your home what linear combination. Just now, our main topic is what are linear dependence and linear independence. So this is the example of this is a theory. This is the definition of linear dependence and independence. It says that if we have a vector S, a set of vectors in a vector space V, and if we are going to multiply and add them C1, C2, C1, V1, C2, V2, and CK, VK is equal to 0. If the equation has only trivial solution, meaning is that if all the C is equal to 0, C1 is equal to C2, CK, then S is called a linearly independent. And the another second thing is, if any one C like this is not 0, then we say that it is a linear dependent. So only the difference between linear dependent and independent is in linear independent we have all the C is 0, and in linear dependent, if any one C is non-zero, then we say that it is linear dependent. So just it is a very minute difference between linear dependent and independent. Now we see the examples of linear dependent and independent. So phi is linearly independent, and if a vector 0 belongs to S and S is linearly dependent, vector does not belongs to 0 and V is linearly independent, and S2, if for, and the fourth point, if we have S1 S2 and S2 contains S1, then S1 is linearly independent, then S2 is also linearly independent. If S1 is linearly independent, then S1 is also linearly independent. So these are, now I will show you the examples of to check whether it is linearly dependent or linearly independent. So we have given a question: determine whether the following vectors are linearly dependent or independent. We have given S is equal to something and check whether it is dependent or not independent. So first of all, I write a linear combination of this. So we know the linear combination can be write like this: C1 V1, C2 V2, C3 V3. As in the previous slide I told you, it is called a linear combination. So I write C1 V1. So with the help of this, I obtain a three equations and three unknowns by any method, either either solve equation 1 or 2, or equation 2 and 3, or we can solve by the Gauss-Jordan elimination method. So any method you can apply, you can solve this. So I'm going to start here. First of all, I write a linear combination of C1 V1, C2 V2, C3 V3. So with the help of this linear combination, I write the three equations. So first I write C1 first I write C1 V1. So C1 V1 yani uh, C1 and V1 yani this is our uh, C1 multiplied by 1 and C2 multiplied by 0 and C3 multiplied by, here we have C1 multiplied by 1 and C2 multiplied by 0 and C3 multiplied by -2. So this is our equation number 1. Similarly, again I, in the jth element, I multiply C1 multiplied by 2 and C2 multiplied by 1 and C3 multiplied by 0. We get a equation number 2. Similarly, the third element, C1 multiplied by 3 and C2 multiplied by 2 and C3 multiplied by 1, and we get the third equation. So we have three equations and three unknown. So either you can solve equation 1 and 2 and then solve equation 2 and 3 and then find the value of C1, C2, C3. Or the another method is write in the matrix form and then you can solve. So write this equation 1, 2, 3 in the matrix form. So first of all, the constant of C1 is, I write the constant of C1 here is 1, and similarly the constant of C1 is 2 right here, and the constant of C1 is 3, so I write here. So in the same manner, I write the whole matrix and then apply the Gauss-Jordan elimination method. Then as we discussed in previous week 2 or week 3, how we can solve this matrix. So our aim is to write 0 over here and our aim is to write 0 over here. So there are some row operations that we have to apply. R2 is equal to R2 minus 2R1. So this type of row operations we have to apply with the help of the, and similarly R3 is equal to R3 minus 3R1. So these are the operations that we have to apply over here, and we get 0 over here. So similarly, again on the second step, we want the 0 in this place. So again, I apply the operation in the next matrix. यानी कि R3 we have to make R3. It is equal to R3 minus 2R2. 2R2. So there are, as you know, in the previous week 2 or just check week 2 and week 3 lecture, I solved too many questions problems like this, and finally we convert this matrix into the in this form. So this form, as I convert it, so directly we can say the value of C1 is 0, the value of C2 is 0, and the value of C3 is 0. So the C1 is equal to C2 is equal to C3 is equal to 0. So remember, if what is the definition of linearly dependent and independent? So remember, in the previous slide I show you the definition of linearly independent is if all the C is are 0, then we directly say that it is linearly independent. If any one C is non-zero, then we say that it is dependent. So in our case, it is all the C's are 0, so it is linearly independent. So hopefully you understand the linearly independence. Okay. So next example of linearly dependent, we check another example of linearly dependent. So there is a question is given. This is the vector is given. This is V1 and this is V2 and this is V3. These three things are given. So check whether it is a linearly dependent or independent. So first of all, we have to write in a linear combination. This is a linear combination C1 V1, C2 V2 and C3 V3. So with the help of linear equation, I have to write three equations. So equation number 1 and equation number 2 and equation number 3. And these three equations, now I'm going to solve these three equations, and using the Gauss-Jordan method, Gauss elimination method, I write it in this form and convert it into the upper triangle or lower triangular matrix. So as I observe that there is a whole row is 0. So when these things are happens, then we say that there are infinitely many solutions. If this time these things are happening, just check the week number 2 or 3. Over there we define if these things are happening, then it is infinitely many solutions. And there are one another case. Remember, if you remember it, if there is some value over here, if for example if there is a value over here like 5 and here are 0 0 in the left side, then on that case we say that the no solution. So there are 3 points, but I think you just check whether on that lecture. But in our case here there are infinitely many solutions, meaning is that we have some values of C1 C2, so it is called a linearly dependent. These are the value of C1 C2 C3, so we say that it is a linearly dependent. So another examples of linearly dependent and independent, these are the examples of matrix. We have given a 3 matrix V1 V2 V3. So first of all I write a linear combination. With the help of linear combination, I am going to solve this the same procedure. Don't confuse with the matrix. The same procedure we have to follow. And similarly, we write in a matrix form: equation 1, equation 2, equation 3, equation 4. and write this in the matrix form, and similarly convert it into the upper triangular matrix or lower triangular matrix. So here again we see that there is a infinitely many solutions are there, trivial solution. The system is the all the equations. This is the value of all are 0, and whole row are 0, and we have how many constants? C1, C2, C3. We have three constants and four rows, and one row becomes 0, and we check that the value of C1 is 0, the value of C2 is 0, the value of C3 is 0. So there are all the values of C are 0. So the system has a linearly independent. So these are some properties of linearly independent and independent. So the another thing is basis and dimensions. So it is very same as basis a vector space V, and if we have a S is a vector space, it is contained in S is contained in V. So if S is linearly independent and S is a span of this, then it is said that it is a basis. So there are these are standard basis. This is standard basis in R4. Standard basis these are, and in R2 we have a standard basis 1001. Similarly in R3 we have a standard basis 100 010. So same, these are the standard basis. So these are some definitions of some numbers of a vector space basis. So these are some definitions. A vector space V is called a finite dimension vector space if it has a basis consists of a finite number of elements. So if finite element, then it is called a finite dimension. If it is infinite, and that infinite dimension, then it is infinite dimension dimensional. And similarly, the dimension of a finite dimension vector space V is defined to the number of a vector in a basis for V. V is a vector, S is a basis. So dimension of V is equal to the basis. So these are some terminologies of basis. You will see. And the coordinates and change of the basis. So these are some same thing like this. We will check. So this is the end of this lecture today's. Over here we discuss so many things. So it is a revision of the today's lecture what we discussed today. So today we discuss, first of all we discuss the vector space, and in a vector space we discuss 10 points. There are 10 points we discuss, and after that I discuss some examples of the vector space. Here there is a question, another question is given that if we have a vector 2 by 2 matrix are given that, and we have to show that whether it is a vector space or not. Two vectors are given, u and v, and we have to show that it is a vector space or not. So what we do, we have to show all the 10 axioms, all the 10 points. So it is showing one by one. So whether it is point number 1 is it is closed under addition. So yes, it is closed. It is belongs to vector space. So axiom 1 is satisfied. Now move to axiom number 2. So u plus v is equal to v plus u. So we are going to add u plus v, and similarly we are going to add v plus u. So we get the same thing. So it is closed. The commutative law hold. Similarly, axiom 3, 4, 5, 6, 7, 8, 9, 10. So we show all the axioms, and over here just like this axiom 4, 0 plus u is equal to u. So it is showing that. Similarly, axiom 5, if we are going to multiply with minus sign, then it is also minus u, and u plus minus u is equal to 0. This is axiom number 5. Similarly, axiom number 6, if we are going to multiply with a constant k, and it is also belongs to v. Similarly, axiom number 10, if we are going to multiply with 1, then we get the same matrix u. So these are the some axioms. One by one we are multiplying with this, and we get the same result. So it is a vector space. Vector space. After that, I discuss uh, examples of vector space. After that, I discuss the subspace of vector space. So this is the definition, and it satisfies 2 points. One point is vector addition, and the another point is scalar multiplication. Because of it is a subspace, so it means it must be satisfied all the properties of a vector space. Meaning is that it satisfies all the 10 points, 10 axioms. After that, it satisfies these more two properties: addition and scalar multiplication. So these are some examples of the subspace. So these are some examples of the subspace. Then linear combination I discussed. These are some examples of linear combination, and this will be the end. So now tell me, what is your question? Mutaib, tell me, what is your question? Let's create a submission for week 5 homework. Okay, submission folder for week 5 homework. Okay. Okay. Yes, yes. For week 5 submission folder, I will create a submission folder week 5. Yes, soon, today or tomorrow, I will create a submission folder. And dear Imam, in your class also, I will this time I will remember. In both the class, I will submit. I will create that folder. Okay. So you will prepare. You will prepare and go study. And one more thing, if you have any problem regarding solving the assignment, and you can come to my office before your class, and you can discuss me. If you face any problem regarding if you are going to solve the assignment, if you face any problem, if you are not understand any question, then come to my office before your class, and then I will discuss. I will give you the solutions, or whatever. If you have any question you don't understand, I will give you the solution of that. Okay. Thank you. And any other question? And inshallah, next week I will provide you the final assignment. The name of that assignment is final assignment, and that will contain 25 to 30 questions, and it is belongs to from week 1 to week 6. And as soon as possible, I will provide you in the next week.